So the next thing we're going to look at that influences yaw stability is the existence of a fuselage. Okay, so here's our center of gravity, and here would be like the center pressure of the fuselage, or a nacelle. This can be a nacelle, an external store. Anyway, this can be any aerodynamically shaped object that's not necessarily a lifting surface. Okay, and we're going to take our approximation again from Hoke, from his I think it's just a K there, from his 1960 publication. So the exact same thing we did in pitch, we can also do in yaw. Okay, so just like we looked at the influence of the fuselage on the pitch, trim, and stability of the aircraft, we can look at it on the yaw, trim, and stability. And so I'm not going to work through all the math. It's nearly identical to what you get in pitch, but I'm just going to write the final solution here. So the yawing moment due to the fuselage is equal to, and this is in terms of global parameters, where that yawing moment from the fuselage has been non-dimensionalized by 1/2 rho v infinity squared SWBW. And so we can write that as a Cn beta of the fuselage times beta. Okay, so we're going to assume that the minimum drag axis is where beta equals 0, and so we're just going to have a term that is proportional to beta, where Cn beta from the fuselage is equal to, and this equation should look familiar to you, SFLF over SWBW times 1 minus 1.76 dF over CF to the 3/2. Okay, so we're just basically saying that that we have some. This is our yaw stability derivative. This is the influence of the fuselage on our yaw stability derivative, and you can multiply that by beta to get the actual yawing moment due to the fuselage. Now you should remember that this is just an approximation, so this is not this is not incredibly accurate, and certainly you want to do full CFD or wind tunnel tests or something like that to get a more accurate approximation. But in initial stages of design, this isn't a bad first step for an approximation.